Think about a nuclear reactor. It is a fortress of steel and concrete, built to withstand earthquakes, floods, and direct impacts. But occasionally, these billion-dollar marvels are forced offline by something entirely lacking a spine: millions of glowing jellyfish. To keep the core from melting down, every thermal power plant on Earth relies on a massive intake of cold water. They pull in millions of gallons a minute from nearby oceans, rivers, or lakes to condense steam back into water and keep the turbine spinning. This map illustrates global water temperatures trending steadily upward over the last few decades. As these coastlines and river basins heat up, they create the perfect breeding ground for massive, rapid biological blooms. Because these plants draw their water directly from the environment, a dense swarm of marine life can easily get sucked into the intake channels. They bypass the seismic shock absorbers and concrete containment domes, physically clogging the filtration systems and forcing the reactor to trip offline in minutes. Grid operators are moving past macro threats like hurricanes or fuel shortages. Today, resilience means winning a daily, highly localized war against shifting physics and opportunistic organisms. When water stays abnormally warm and clear, aquatic plants and invertebrates go into overdrive. Species like Jellyfish selves or fast-growing eelgrass thrive in these new elevated temperature baselines. Look at this dense thicket of eelgrass growing in the Wheeler Reservoir in Alabama. In the summer of 2020, a massive, unexpected surge of this specific grass broke loose, drifted toward the Browns Ferry nuclear power plant, and choked the water intake, forcing operators to shut down 2 reactors. The mechanical consequence of this biology is immediate. As the water rushes in, drifting plants and marine life slam against the giant rotating drum screens designed to filter out minor debris. When the biomass gets too thick, water flow stops completely. This giant pile of small fish and barnacles had to be removed from the Karachi cooling water filters in 2023. The volume of organic material gets so extreme that standard automated cleaners fail, requiring crews to manually extract tons of biomass just to reset the pumps. This photo reveals a metal drum screen mesh at the Torness power plant in Scotland. The sheer differential pressure created by the blocked water flow physically ripped the heavy steel mesh apart. A reactor can generate gigawatts of carbon-free electricity for decades, but its operational lifespan depends entirely on an unobstructed flow of liquid. It is physically subservient to the biological health of the ecosystem surrounding it. Milder winters are actually making cold weather operations more dangerous for many water-cooled power plants, thanks to a counterintuitive anomaly. They are dealing with Frazil ice. Instead of freezing into a solid sheet, turbulent water instantly crystallizes into millions of tiny, sticky ice needles. This cross-section shows the meteorological trigger. When heavy winter winds meet clear skies, a traditional solid layer of surface ice fails to form. Without that solid cap acting as a thermal blanket, the wind rapidly strips heat from the exposed river. The liquid actually drops below the freezing point, entering a supercooled state. Because the wind is churning the water so violently, it can't freeze solid, so it remains a chaotic liquid slush of suspended crystals. When that supercooled slush gets sucked into the plant's intake, the sticky crystals bond to the cold metal grates. They multiply rapidly, bridging the gaps and sealing off the water flow like concrete. Decades ago, engineers designed these facilities expecting stable, solid winter ice cover. The disruption of those predictable baselines has exposed a fatal design blind spot. Operators know that passive steel nets and screens are no longer enough. To keep the water flowing, they have to deploy active, dynamic defense systems. One method is the air bubble curtain. High-pressure compressors pump air through perforated pipes laid on the seafloor. The intense upward force of the bubbles creates a physical wall that gently shoves buoyant jellyfish and debris away from the intake channels. To stop Frazil ice, plants use a thermodynamic solution by retrofitting massive recirculation pumps. Warm water expelled from the reactor's heat exchangers is piped directly back to the freezing intake, artificially raising the local temperature just enough to melt the slush. Sites are also deploying acoustic sensors and continuous AI-driven camera feeds to track water turbidity, algae concentration, and fish migration. The goal is to detect incoming swarms and throttle down the reactor before the filters clog. We are moving from an era where critical infrastructure sat passively in the environment to an active defense posture. Power plants must continuously push back against the surrounding ecosystem to maintain operations. But there is an upper limit to how much heat a plant can handle. Extreme summer temperatures cripple a reactor's thermal efficiency, and environmental regulations force operators to reduce power if the discharged water gets too hot for local rivers. This split cycle diagram illustrates a concept called ice thermal storage. At night, when grid demand and temperatures are low, the plant uses cheap electricity to freeze a massive, centralized reservoir of water. When the sun comes up and air conditioner loads spike, the melting ice block provides an enormous surge of supplemental cooling. By shifting the cooling burden, the facility avoids daytime water temperature limits. The reactor continues operating steady at 100% capacity, precisely when the regional grid is pulling the most electricity. The stakes here are absolute. As we saw during the deep freezes in Texas, when thermal power plants fail due to weather, the entire balancing authority risks total collapse, leaving millions without heat or water. Meeting the 21st century's demands means looking beyond new generation alone. It forces us to re-engineer the legacy machines at the foundation of our grid to withstand an increasingly hostile natural world.